Hello everybody, this is Dr. Nur Badshah from University of Engineering and Technology, Peshawar. In this video, I'll be talking about application of ordinary differential equations. In the first part of this video, I'll talk about application of ODEs in electric circuits. So I'm specifically talking about LRC series. Let's suppose in that LRC circuit, I represent the current, right, and the voltage drops across the inductor, resistor and capacitor. They are defined in the following way. We know that by Faraday's law, L into di by dt, or we can say that L d square q by dt square, that's the voltage drop at any inductor. By Ohm's law, the voltage drop at a resistor is equal to I times R, or we can say R times dq by dt, whereas the voltage drop at a capacitor, that is defined as q by c, or we can write 1 over c integral from 0 to t I of t dt. Now by Kirchhoff's second law, we know that sum of these voltage drops is equal to the input voltage, which is E of t. Mathematically, we say that L times di by dt, that's the first voltage drop, that's the voltage drop at an inductor, plus the next voltage drop, which was defined as IR by Ohm's law, that is the voltage drop at a resistor, whereas Q by C is the voltage drop at a capacitor. So by Kirchhoff's law, sum of all these voltage drops should be same as the input ones, that is E of t. So if you want to find I and Q is given, so we'll be using this formula, where Q might be replaced with the integral function, like Q is equal to integral from 0 to t I t dt. So this equation might be written as L di by dt plus Ri plus 1 over c integral from 0 to t I t dt, that is equal to E of t. This equation may be converted in terms of voltage variable as well, where I is basically what? That is dq by dt, we know that. So the first term, that is L di by dt, that will be replaced with d square q by dt square plus R dq by dt plus q divided by c. We just replace I with dq by dt in the first equation. We can have another expression if we want to express everything in terms of current I. Okay, so we can simply differentiate this one again. So if we differentiate, this becomes d square I by dt square R times di by dt plus 1 over c dq by dt, and that will be E dash. So we can have another equation as well, differential equation as well, that is Li double dash plus Ri dash plus 1 over c, and that is I. So in this case, you see that the differential equation is totally depending on what? An I. Right, so we can use this equation as well if you want to find current at any time in the given circuit. So let me solve some questions where we would apply these differential equations for determining voltage, or we may be determining the current in the circuit, or we might be interested to determine the uh, charge in the circuit as well. That's the LRC, which involves obviously inductor, a resistor, and a capacitor. Okay, so let's do some questions or some examples. It says determine the current I of t in a single loop LRC circuit where L is given as 0.1, R is 2, and C is 0.1. Initial condition that is given is I of 0 is equal to 0, and the impressed voltage, the input voltage, is given as E of t is equal to 120t minus 120t into ut minus 1. We may call sometimes as a rectangular input. So in this case, the differential equation will be L di by dt plus Ri plus 1 over C integral from 0 to t it dt, that is equal to E of t. Now putting all these values in the given equation, this differential equation will become L is equal to 0.1, so we can write 0.1, and this is di by dt plus R is 2, so we have 2i, plus C is 1 over 0.1 integral from 0 to t I of t dt is equal to 120 t 120t ut minus 1. We are keeping in mind u is what? That's the unit step function. We may simplify this with multiplying by 10. So we have what? We have, this is simply 1. So we will be having di by dt plus 20i plus 100 integral from 0 to t it dt is equal to 1200. We may write that as t minus t ut minus 1. Now what do? We apply Laplace transform on both sides to solve this differential equation for I, because we are interested in finding current in the given network. So Laplace of di by dt Laplace of di by dt 20 times Laplace of I, 100 times Laplace of integral from 0 to t it dt, 1200, it will be Laplace of t minus Laplace of t ut minus 1. So by using that rule, Laplace of di by dt can be written as s times Laplace of I minus I of 0, 20 times Laplace of I, 100, and Laplace of integral is what? That is 1 over s Laplace of I, 1200. Laplace of t is 1 over s square, whereas we will be applying second shifting theorem. So in this case, gt minus 1 is given as t, so g of t will be t plus 1. That means in this case we will be taking 1 over s square plus 1 over s into, you see, because of the unit step function, we will be taking e power minus s. right? So that's the Laplace transform of t ut minus 1. Okay, now you see we can we may multiply this with s as well, because just to get rid of this s. So multiplying by s, this becomes s square. This is 0, so it's 0. Come on, it's Laplace of I just forgot I, minus 0 plus 20s Laplace of I plus 100 Laplace of 100 Laplace of I, because this s will cancel with it, whereas the right hand side becomes 1200 into 1 over s minus 1 over s e power minus s minus e power minus s if you multiply by s. So the left side may be written as, this is s square plus 20s plus 100, s square plus 20s plus 100 into Laplace of I, that is equal to 1200 1 over s e power minus s e power minus s. This is basically s plus 10 whole square. So dividing both sides by this one, then later on I'll do that. So we have s minus 10 square Laplace of I, that is same thing as we have. Okay, so we have this implies, let me write that again, s minus 10, if I've done that rightly, yeah, s plus 10, it's not s minus 10, my fault. So it's s plus 10 squared Laplace of I, that is equal to 1200. Then we have 1 over s minus 1 over s e power minus s minus e power minus s. I think it's the same thing what we have, 1 over s minus 1 over s e power minus s minus e power. Now dividing this by s minus 10 square to get Laplace of I, 1200. This will become 1 over s into s plus 10 square minus 1 over s into s plus 10 square e power minus s, 1 over s plus 10 square e power minus s. Now we can use partial fraction again here to find the value of to factorize this one or to make a partial fraction of this one. और ये दोनों क्या है, दोनों सेम है. सो इसका Laplace ट्रांसफॉर्म फाइंड करेंगे कैसे. It can be done in the following way. 1 over s plus 10 square, we write that as, to find the value of a for it, so simply take 1 over s plus 10 square, s is equal to 0, 1 over s plus 1 over s, s equal to minus 10, and then we have s plus 10 square plus maybe a divided by s plus 10. That's a shortcut method. So putting this value in here, we get what? When you put s equal to 0, that gives you 100. So we have 1 over 100 into 1 over s. If you put 10 here, so we get minus 1 over 10 into 1 over s plus 10 whole square. And then we have a divided by s plus 10. On the left side, we are having 1 over s plus 10. So we can put any value. The left side is what? That is 1 over s into s plus 10. We want to find the value of a. So you can simply put s equal to anything. Let me put s equal to minus 9 just to get a very simple value here. It could be anything. The left side will give you minus 1 over 9 because this will give you plus 1 square is 1. It is minus 1 over 90. This will be 1 over 10 because again if we put 9, so we get this one. And this will give you minus a. Plus a, sorry. Because minus 9 plus 10, that will give you a. So if we simplify this, we will get the value of a, which is minus 1 over 9 plus 1 over 90 plus 1 over 10. So the value will be, you can simplify, LCM is 90. So this is minus 90, this is plus 1, this is plus 9. So which will give you minus 80 by 9, which give you 8 by 9. So a is basically equal to minus 8 by 9. So altogether this becomes what? Laplace of I is equal to 1200. This can be replaced by 1 by 100 divided by s, 1 by 10 divided by s plus 10 square, minus 8 by 9 divided by s plus 10. The same thing with this one as well. You would just repeat the value, only the difference will be multiplying with e power minus s, minus that will become again 1 by 100 s, 1 by 10 divided by s plus 10 square. Then we have minus 8 by 9 into 1 over s plus 10 e power minus s. And then we have minus 1 over s plus 10 square e power minus s. So we are interested to find I now. So I of t will be Laplace inverse of all of them. So I just go for the Laplace inverse directly. Laplace of inverse of this one is what? That is 100, 1 by 100. This will become, if you see, is 1 by 10 s plus 10 square. So using first shifting theorem, it will become 1 by 10 t e power minus 10t. This is simply 8 by 9 e power minus 10t. The same thing with e power minus s, so that will give you what? Minus 1 by 100, 1 by 10, it's t minus 1, e power minus 10t minus 1, 8 by 9, e power minus 10t minus 1, and then you would simple write with it to ut minus 1. That's a unit step function. The same thing here, if you see that is minus t e power minus t, but we'll just take t minus 1 e power t minus 1 ut minus 1. So that's the solution of this differential equation, and that's the I of t, which can be obviously simplified as well for t less than 1 what is going on, and for t greater than 1 what is going on. You can just simplify that as well. Okay, we can do same thing for the following information. So again we are interested to find I in it. So L is given. Okay, so the equation will become what? L is 0.1 into di by dt plus R, that is 3 into I 1 over 0.05 integral from 0 to t I t is equal to et, which is 100, and now we have ut minus 1 ut minus 2. So again this is what? This is 1 by 10 Laplace of di by dt 3 times Laplace of I 1 by 0.05, that is 20, and Laplace of integral from 0 to t dt I dt this is 100, and Laplace of ut minus 1 will be e power minus s e power minus 2s divided by s divided by s. This is known as first shifting theorem, second shifting theorem, t shifting, sorry. Now what we do, we just simplify this one. It is 1 over 10, keeping in mind the condition is given that I of 0 is equal to 0. So it's 1 over 10 Laplace of di by dt will be s Laplace of I minus I of 0, which is 0, plus 3 times Laplace of I, and then we have again the same rule, 20 1 over s, and Laplace of I is equal to 100, and so on, blah blah blah, same thing. Now what we can do, we can simply multiply this by 100, sorry 10s, just to simplify the thing. So multiplying by 10s, this will cancel, so we get s square Laplace of I, this is 0 because given at 0, plus 3s 30s Laplace of I plus 200 Laplace of I is equal to 100 000, and s will be cancelled with each one, so e minus s e minus 2s. This could be written as s square plus 30s plus 200 into Laplace of I is equal to 10,000 e power minus s minus e power minus 2s. Okay, so we can factorize them, or we can find the factors. So we need to find Laplace of I, that is equal to 1000 divided by s square plus 30s plus 200 into e power minus s e power minus 2s. Right, so the rest can be done exactly in similar way by factorizing this. How could we factorize this? 1 1000 divided by s plus 10 into s plus 20 into e power minus s e power minus 2s, or Laplace of I, that is equal to so it's 1000 divided by 20 minus 10, and we have 1 over s plus 10 minus 1 over s plus 20 e power minus s e power minus 2s. It is just a partial fraction by using a shortcut method. This is 1000 divided by 10 into 1 by s plus 10 minus 1 by s plus 20 e power minus s minus again 1000 by 10 1 by s plus 10 minus 1 by s plus 20 e power minus 2s. Now they can be cancelled. This one, the same thing here will be cancelled. So we need to find I, that will give you Laplace inverse of 100 1 over s plus 10 1 over s plus 20 e power minus s minus 100 Laplace inverse of 1 over s plus 10 s plus 20 e power minus 2s. Now by using second shifting theorem, we can write that is 100. Laplace transform of this is e power minus 10, and because of e power minus 1, that will be t minus 1 minus e power minus 20, again t minus 1 multiplied by ut minus 1. It is because of this e power minus s. Similarly, 100 e power minus 10 into t minus 2, because of this 2, e power minus 20 into t minus 2 multiplied by ut minus 2. Right, so it can be taken again in a piecewise defined function form. We can take that as I, it will be 0 when I is less than t is less than 1, sorry. Its value will be this quantity when t is between 1 and 2. So that will be 100 e power minus 10 t minus 1 e power minus 20 t minus 1. And for t greater than or equal to 2, we'll be taking complete this function except the ut minus 1 and ut minus 2. The minus 100, the next one as well. So that will be solution of the equation. Okay, so that's the equation. Solution for the equation to find the current. Next one is find the output voltage response with the resistance that's 20 ohm, L is 1 Henry and C is 10 power minus 4 Farad. The input is delta T, which is also known as a unit impulse, and current and charges are 0 at time t. In this case, what do? We are basically using the second form of the equation, that is LD square q by dt square plus RdQ by dt. From here we would find what? We would find Q, and then from Q we can find output voltage as well, because you know that voltage is also what? That is Q by C. Okay, so what do? The process is same. First we put the value R, L and C. So you put in the value, L is what? That is, in this case L is 1, so this equation will become what? D square Q by dt square. R is 20, so 20 dq by dt plus 1 divided by 10 power minus 4, or we can say 10 power 4. Q is equal to, this is the response, which is delta t. So we just write delta t here. Now applying Laplace transform, it will give you Laplace of, with condition, keeping in mind that I of 0 is 0, whereas Q of 0 is also 0. In fact, I is what? That is dq by dt, so this condition can be written as q dash 0 is equal to 0 as well. So applying Laplace on both sides, Laplace of q double dash 20 times Laplace of q dash 10 power 4 Laplace of q, and Laplace of delta t is e power minus s. Putting all these values, this is s square Laplace of q, the rest will be 0. We know that it is minus s q of 0 minus q dash 0. This is 0, this is 0 given in the statement, plus 20 times Laplace of q, which will be s times Laplace of q, minus q of 0, again it is 0, 10 power 4 Laplace of q, e power minus s. Now this can be written as s square plus 20s plus 10 power 4 into Laplace of q, e power minus s. This might be written as s square 20s plus 100 plus 9000. In fact, it's 9900 Laplace of q is equal to e power minus s. So the first part is what? That would become s plus 10 whole square plus 9900. You may confirm this 9900. Laplace of q is equal to e power minus s. Or we can say Laplace of q, that is equal to 1 divided by s plus 10 whole square 9900 into e power minus s, which implies Laplace of q is equal to, if I go back, so that is 1 by s plus 10 square plus, if it is right, 9900 under root square. So we need this quantity here as well. So we'll doing same thing here as well. E power minus s. So we are interested to find Q. So Q is what? That is Laplace inverse of 1 over under root 9900 into under root 9900 s plus 10 square under root 9900 square e power minus s. Now using shifting theorem, the first shifting theorem from here, that will give you 1 over under root 9900 sine e power minus 10t into sine t by under root, this is sine under root 9900t, with t is t minus 1 ut minus 1. That's basically the shifting theorem. So altogether we have 1 over 9900 e power minus 10 into t minus 1 sine under root 9900 t minus 1 ut minus 1. But voltage is what? Voltage drop is, or whatever output voltage is, V is equal to Q by C. And this is found as Q. So we have now V is equal to 1 over C was 10 power minus 4 into Q. So we can simply multiply this quantity by what? Or you can say 10 power 4 10000 Q. So we just multiply this with 10,000, right, to get the value of this voltage. Thank you very much for being with me for so long. See you in next video with next application of ODEs with Laplace transform. Thank you. See you next time.